Good afternoon, everybody. My name is MD Nizam, and I'm a PhD student in University of Louisiana at Lafayette. And our research title here is Deep Learning Aided Software Vulnerability Detection, a survey, and it's been conducted with Yihe Zhang and Dr. Xiali. Nowadays, cyber attacks has been prominent, and research studies have shown that yearly 8 million victims has been affected by this type of attacks, and on an average, $2.6 million has been lost for each incident. So these attacks are mostly due to the software vulnerabilities or the bug that are exploited by the cyber attackers. And to mitigate those bugs or vulnerabilities, it's very important to detect those and solve those in the development phase or later on. So like traditional methods, static, dynamic methods has been used for quite a long time. Also, fuzzing has shown some promises in this regard. But like every of those has severe limitations, ranging from false positive to slowness or a lot of manual intervention requirements. So in order to remove the manual interventions, it's required to do something that automatically detect the vulnerabilities. From the recent decades, deep learning has shown promising results where it has like classified or detected vulnerabilities. So here we are going to survey and systematically gather and research the recent studies. So the recent reviews on this field lack unified framework. So we need a comprehensive review of this field, that is deep learning based vulnerability detection. In this study, we introduces a 6-phase life cycle framework, and we analyze 34 studies from 2027 to 2024, and we systematically revise their work and utilize in our research. So our research method. So first we define the DL-based source code vulnerability detection, its life cycle, and we select the groundbreaking and impactful studies from 2027 to 2024. We have initially came up with 94 studies and finally narrowed down to 34 studies that were relevant to our topic and research. So in selecting the studies, we have followed 3 criteria: novelty, citation count, and foundational impact. So we have first found out that which work was very initial and provided novelty. Then we have checked their citations, and in our research we have found that like one of the our top paper citation was 1300 plus, to the lowest citation was 200 plus. Then we have considered the foundational impact. We have found out that a few of the works has been used as a benchmark or some other works has been extended from those particular work. So logically, we have put those studies in our research. So we have analyzed their methodologies, and we have found out and sorted out their challenges. Also, we have worked on their research gaps, and based on their research gaps, we have created our future direction, and that this field is lacking. First, we will talk on our vulnerability detection lifecycle that we proposed. This lifecycle consists of 6 phases. Uh, First one is the dataset construction, and based on that dataset construction, we have to first come up with the detection of vulnerability granularity. Then we have to represent the code in such a way that machine can understand. So our third phase is the code representation. Then we have to feed those represented code to a model. So we have to design the model, which comes to our fourth phase of the life cycle. And the fifth one is the model performance evaluation. After the model performance is evaluated, uh, we are proposing that a real-world project implementation is required to find the efficacy of the model. So our first component in our life cycle is the dataset construction. So in our work, we have gone each of the component of the life cycle, and we have found out that the other groundbreaking works, how they worked on that particular phase, and how they worked within that cycle, and what are the challenges still remained on that particular cycle. So in our dataset constructions, we have collected and presented like 11 mostly used dataset on this field. So we can show that the source code language of the data they are presenting, and the type of data they have used in their studies, also the source of the data they have collected. And here from this table, we can show that a few of the dataset has got a good number of test cases. Like one of them is D2A, which has a total sample of 1 million plus. Like if you talk on the source of their dataset constructions, we have found out that the most prominent source was the NVD, the National Vulnerability Dataset, CERT, and GitHub or GitLab, like open source projects where they have curated the data. In this phase, we have detected like few challenges that starts with data duplication and data set imbalance. I'll go a bit fast forward on this. So if we see that like among our data sets, data set imbalance is very prominent, where like vulnerable and non-vulnerable code percentage differ in quite a big way. Like in one dataset, we can see that the number of vulnerable code is just 1% of the total dataset, that extend from 1% to 50%. The next challenges we identified here is the synthetic bias, like few of the data sets and their data was constructed from synthetic data. That means those are not real world or real project data. Those are just generated based on certain rules. And based on those rules, they have curated some data for their model training. Next limitation, we have found out that limited types of common weaknesses. So vulnerabilities, its type and its depth can vary. So most of the dataset just covered like top uh, 30 or 40 type of vulnerabilities, which lacks in a great deal and misses a lot of vulnerabilities type. Those can be very dangerous in the real world production scenario. The next, we have found out that the language diversity is most likely your C or C++ language. Like only two dataset here, we have found out that covered Java, that's Juliet. That is also a synthetic dataset. And one other dataset that covered is Java is the last one here. Our next phase of the life cycle is vulnerability granularity detection. And to detect the vulnerability of a source code, we need to find out the level or depth where we can detect the problem. So there are a few places we can segment it in detection level. We have worked with like 4 levels, and most of the studies has followed this one. In any of the level, they have tried to detect the vulnerabilities, like it can be in a file or in a function, in a slice or in a token. So we have found out that these challenges here are mostly LIW and LIT. We have came up with these terms like lost in the woods. We are calling this problem is LIW, Liu problem. That is suffered by L1 and L2 level detection, where file and function level we are calling it. Like a file and function, they can contain like hundreds of thousands of line of code. So if we say that the detection level is file level or function level, that means it's very hard to detect or pinpoint the problem, and it requires a lot of human intervention to go down to the where and find out the original problem. So we call it a lost in the woods problem. The next two level, slice and token, they suffer the lost in translation problem. That is, we term it LIT, lit problem. Like when from the source code, slice and tokens are generated, sometimes it loses its syntactical meaning. So in that case, we are calling it the problem has occurred in the lost in translation problem. So these are the two challenges in vulnerability granularity definition. And also the balancing precision with semantic context is very critical in this phase of the life cycle. Our next life cycle segment is code representation technique. Once we detect or select the level of detection, we need to represent the code in such a way that we can um, convert and feed it into the model. So the main goal of this phase is to capture the syntax and semantics of the source code well, so that the model can learn and predict. So across the studies, we have found out that 5 type of methods that studies have used. One is AST-based representation, another one is graph-based, hybrid, NLP-based, and embedding-based. In AST-based representation, uh, the studies have shown that source code can be represented in a tree-based structure where each node can have the information of the source code with the syntax structure, but they sometimes do lacks the semantics. In the graph-based, the code has been presented in a graph structure where syntax and syntactic semantic meaning are captured, and also their dependencies are also mentioned and well structured there. In hybrid model, both of the AST-based and graph-based, those are combined, and it's quite a bit a strong method we have found out across the studies. Also in NLP based, they have mostly resorted to the NLP techniques to capture the semantic meaning of the source code. In embedding based, they have used the different embedding techniques, and they also put the succinct numerical depiction so that the model can learn. The challenge we have found in this phase is it's quite a tricky thing to matching the models to the appropriate representations. We have proposed a novel comparison mechanism to compare these 5 techniques. It's a new numerical value we have come up with on 3 criteria. That is a syntactic, semantic, and complexity of each technique. And for this, we have proposed the MCDA, that we call it multiple criteria decision analysis, and weighted decision matrix, WDM. And by using these 2 methods, we have generated the formula to calculate their scores, like to get the syntactic score of AST-based or graph-based. We have used the structural fidelity, the granularity, and the adaptability. Also for semantic score, we have used data flow modeling, context awareness, and scalability. And for the complexity score calculation, we have used computational overhead and ease of implementation and scalability. So based on these, we have ranked and scored the 5 technique, and our method have shown that the hybrid technique has the overall best score in this regard, though the AST-based method have shown superiority in the syntactic field. Next, we'll talk on the model design phase, where the studies have proposed various type of model and their design. So they have more or less used three types of vectorization techniques that ranges from one hot encoding, word to vector, and doc to vector. And based on these, we can show that the existing studies have three major model selections. One is sequence models, the graph models, and the hybrid models. From the sequence models, we have found out that mostly used models was RNN, LSTM, BLSTM, and GRU, where the sequence models are based work with the sequence type of data. In the graph models, we have found out that AST and graph-based representation have worked well on those models, and mostly used models here as are GNN, GCN, and GAT. In a hybrid model, two type of models and their facilities have been combined. And in this phase, we have found out that all the studies have faced the high compute cost and poor generalization. In this table, we have summarized the works where we have shown their studies, their corresponding type, what type of model they are using. It can be sequential or graph-based or the hybrid one, and their models, which model actually they used, like three of them use the BLSTM and two use GNN. And also we have shown their implementation mechanism, like this particular work has used the TensorFlow and Python, and this particular work has used the TensorFlow with Keras. Also, we have put down here their features with their corresponding challenges. Our next phase of the life cycle is model performance evaluation. Across the studies, we have found out that the metrics they have used to quantify their results are accuracy, precision, recall, F1 score, FPR, and FNR. So if we talk about the results, like they have, some of them have provided quite a promising results from a detection level to like a precision level to 92% at most. And the challenges we face in this phase of the life cycle is we haven't seen any unified or standard performance evaluation metrics. Like different studies have used different type of metric to quantify their results, but this field require a standard set of metrics by which we can identify their efficacy and their results. The next phase in our life cycle is real world project implementation. So we have seen that few studies have worked well with their data, and they have pretty good performances on detecting vulnerability, but most of them haven't tested their model on real world project so that we can find out that how their model or system works on an unknown data or unknown set of information. So only few of the works they have tested their model on unknown projects, real world projects, and these are the cSphere, Waldpaper, and Waldpaper. So it's been a challenge in this field, and it's a major setback that the studies haven't tested their product on a real world uh, test cases or the projects. So if we summarize our study, we can see this from this table, and from their dataset constructions percentage to their granularity level to their real project implementations. We have put everything in one table to have a better idea of the entire work. As we are talking on the real world implementation, project implementation, one of the particular work that cSphere, they have shown that they have detected 15 vulnerabilities from real world 4 software products from GitHub, and they have reported those vulnerabilities to the authors, and those were later patched and solved. Also, 2 other works have detected 4 vulnerabilities and 16 vulnerabilities respectively. So based on the challenges we have identified across studies, we have projected the future research direction. So the first future direction we are giving here is to make a real-world representative dataset that curate diverse work and diverse set of data that encompasses quite a good number of vulnerabilities type, and the balancing of the granularity detection for precision and performance is very important. So we have suggested to select the granularity in such a way that it curates the dataset well and fit into the model perfectly. Also, we have proposed the standardized benchmark and evaluation metrics that need to be established for this particular field of study, and to measure the model performances. The real world frameworks is necessary where the product will be tested on real world projects. So this project setup will be quite a good advancement in this field of studies. So in summary, we have a surveyed 34 impactful DL-based vulnerability detection studies, and we introduced 6-phase vulnerability detection lifecycle. We analyzed the key issues in all the 6 phases. We provided the roadmap to future research direction in this domain. And thank you.